Hello and welcome to the second video in my Arduino Uno tutorial series. This is a tutorial series in which we learn how the Arduino Uno works. And in the last video what we've talked about is the Arduino in its details. So in general what we talked about is the microcontroller, what microcontrollers are and what the Arduino in particular is. Now in today's video I want to go a bit more into the hardware development platform of the Arduino, because currently we have only discussed the microcontroller and the general metrics, but not actually what the Arduino is capable of in terms of the ATmega on the Arduino hardware development platform. And after we talked about the hardware, I want to quickly introduce you to our starter kit. And when we know our starter kit, we're going to go into the Arduino software and in the Arduino IDE, and we're going to explore how we can write a small program. Now, talking about the small program, what is the goal of the video today? So let's see. Now, what is our goal today? Now, today we want to use the built-in LED. I have talked about that in the last video, that we have a built-in LED on the Arduino. And what I want to do is I want to take this built-in LED and, well, I want to use it. I want to make it blink. And, well, I don't even need to make it blink, because the default application, when you buy an Arduino and you turn it the first time on, the default application that's on the Arduino is a software that makes the LED blink. So instead of actually going in and writing everything from scratch, which we would need to do, we would buy an ordinary microcontroller without the Arduino software. Well, we need to do something to write code. But on the Arduino, well, we don't need to. It comes with a default application. If you start the Arduino, it comes with the same application already open, the IDE, in the IDE on the desktop. And, well, what we want to do is we want to go in and actually understand how this default program works. And kind of like to understand how it works, we will actually go and make a few changes on the default program and make it even better, so it's a bit more usable. I want to show you a few examples of the C++ programming language and how you can use it to kind of like make this all a bit better and understand how it works and kind of like deal with it. Now let's say hello to the Arduino. Now you already know the diagram. We already take a look at this one in the last video. It was a different one, but this is kind of like the same one, but this is like from the Arduino official homepage, arduino.cc. We already taken a look at that one, and we also taken a look at the actual like microcontroller on video, so the actual platform, the hardware. Now, this is a bit more a functional block diagram. This is actually showing you all the features that the Arduino board gives you. Because I've talked about that the Arduino is the chip in the middle, or not the Arduino, the ATmega, the MCU is the chip here in the middle. And this chip has these legs, and to these legs we can connect peripherals, some LEDs, and all of this funny stuff, like components, other external electrical components. And the Arduino board, everything that's on here and there, this is also just some auxiliary stuff that's connected in a certain way to the Arduino to make it interface with something. For example, there's a power supply that converts a broad power supply with a special circuitry to a certain power that the Arduino can take. There's a crystal on here that acts as a clock signal for the microprocessor. There is a chip on here that is actually handling the communication with the computer. There's USB. If you want to program the Arduino, you use USB, and this chip is actually doing the communication with the Arduino and tells it, hey, this is the program that shall be put onto the chip. You can also talk through this chip with your application that's running on the Arduino while the microcontroller is running. So if this chip is not programming, it can still talk to the microcontroller and tell it what to do. We have status LEDs on the board. Like, all of this auxiliary stuff is something that has been predefined on the board. And, well, if this would not be a full hardware development kit, this would be all. Because one board, one feature. However, this is a hardware development platform. So what you want to do is you want to actually connect your own devices to it and kind of like make them run on the code that you write. And for that, you have these pin headers, this one and this one. These pin headers are basically meant for connecting other components to it. For example, here on the top you have the kind of like auxiliary stuff. You have an unused pin, you have an IO ref pin, the reset pin, which acts the same like this button. You have an output of the power supply, you have actually a input of a power supply. So if you don't want to use the power supply here, you can directly power it from an external device. You have ground references, so you kind of like have all the kind of like auxiliary stuff that not directly interacts with the Arduino, or not directly interacts with the chip itself, but kind of like interact with the Arduino, like giving it power and stuff like that. Now what you then have, you have the actual connections to the microcontroller. For example, these 1, 2, 3, 4, 5, 6 pins down here are more or less directly wired to the Arduino's chip, so to the ATmega, to kind of like access the features. The same goes for all of the pins here on the right. They are also directly connected. No, not completely, and more or less. Some of them are also like some reference and ground voltages again, but in general, these are most of them directly connected to the MCU. And this is kind of like the feature of a hardware development platform. You have a lot of auxiliary stuff that is built in, and then let's say 10% is built in. You have the other 90% free for your own usage. So if you want to connect something to the ATmega 328P, you connect it through this pin headers. For example, you can connect an analog signal to this pin here. This pin is basically the pin called PC0 on the ATmega itself. Since we do not go into the details on how the chip internally work, and we are, at least on this tutorial series, stay at the conventions of the Arduino, you can actually see the alternative pin names of the Arduino on the right. So for example, if you want to use it for a digital signal, this is kind of like the digital notification of the Arduino. Also here, analog pin. This is all like kind of like the things that are used on the Arduino side. Digital, analog, and maybe even these like default stuff. Kind of like which is the default usage, how it's default configured. And on the right, what you can see, there's this other orange color. This is the microcontroller's port. So if the microcontroller's port, this is relevant as soon as we're getting into the next tutorial series where we use the AVR coding style, so where we're not using the Arduino software library, where we just use the Arduino as a hardware, then we can reference this microcontroller port with these orange labels. However, we are on the Arduino, so we have it easy. We can select the digital or analog pin. So if I want to use that one in an analog way in the Arduino software, I use analog functions, and I am referencing this with the pin name A0. The same goes for digital, right? If I want to use this as a digital function, then I use internally in the Arduino software all the digital function calls, and the reference is then the pin D14, or in short, these are like 0 and 14. And depending on how I kind of like interface with the Arduino software, I can use these numbers and kind of like give the Arduino software the number, and then, well, use this number to control the output. And this is basically how it works. So let's now actually jump over and take a look on how this all looks in reality. So let's switch over. This is all my stuff that I have for the Arduino, except the bottle opener that I have here. That is actually not something that should be there. I haven't seen it. But this is like all the stuff that I'm using for this tutorial. So what I have is, I would recommend you getting one as well, a multimeter. It is not 100% required that you use one, but this is very easy to kind of like find issues in your circuit, or to quickly just measure if the Arduino is outputting a voltage, right? If you have voltage output and maybe the LED does not light up, something is wrong with your circuit. If the output has no voltage applied to it and the LED is off, then we probably know that maybe the Arduino is not controlling it. Could also be a fault in the circuit, but I don't want to go too much into the details. Right, it's good if we have one that we can measure, but we're not going to directly really hardly depend on it. Same goes for tools like that, some pliers. This is also, no, some pliers and cutters. I don't have pliers here, but I have a cutter here. A cutter is something really useful if you are working with the components coming with the starter kit. But also, you should have one. You can buy whatever you want, or yeah, what you want. Same goes for this thing. This is for breadboards, for building debugs, not building, but like building maker circuits. If I use that one, I can easily bend the pins of components with this one. Also, you don't really need it. I have one. Then we are getting to the main components that we are using. These are the wire kits that I have recommended. This one is, you have some of these in there, but I always have some spare ones laying around because you can never have enough of them. These are the ones that I would highly recommend you, which I already talked about in the last video, the jumper wire cable kit. These are basically some wires that are already pre-cut to a certain length, and they already have bent legs, bent lengths. And also a very good feature of them, they are isolated and they are compact. So if I put these in a circuit, it's going to be quite easy to put them in. I can put them over each other. These kind of wires is the ones which you need to build clean circuits on a breadboard, on a prototyping board. But also, let's put them aside. If you don't want to buy extra wires, everything is in here, including wire. So what is inside of this box from the Arduino? Well, it comes with a CD with all the documentation, which is also available online as far as I know. And then it comes with a lot of components. And I initially wanted you to walk you through each component and tell you what this component is and what it does. But when I have initially recorded this and could go through every component, I think like an hour was over, because there's actually so much to talk about on each of these components that I don't want to go too much into the details. So what we're going to do, it is like agile project management, right? We're going to do and explain them as soon as we're getting to it. Maybe just as a quick overview, what kind of components we have. We have inside of here, we have resistors. This is a quite common components. Here is a set of wires and a bit of motors. Here are some small passive and active components like LEDs, capacitors, what do we have? I think a few sensors, potentiometers are in there, a buzzer, and some integrated circuits for like driving motors, or I think maybe a port expander or something. I haven't taken a look at what they are. Then what we have is we have our main prototyping stuff. So the Arduino itself, a shield for the Arduino, so a board that you can actually push on top of the Arduino using the pin headers, that has a small prototyping board on it. Underneath we have here in this box, not this is some other stuff, some keypads and RFID stuff. We have the main prototyping board, which you're not going to need from day one, so I'm not going to take it out. We have also this one, I think it's a power supply for the board, where you can connect the battery or this wall adapter. There are displays in here, there are more sensors in here, motor drivers, joysticks, battery with battery tab, there's some remote control in here, and also some more displays. Also here a bit of RFID. But that shall be everything. I don't want to go too much into the detail. Let's take out what we need. For this video we actually need nothing from in here. We only need the Arduino out of this box. And, I forgot that, there was actually a USB cable that was also in the box. I've already taken that one out. This is the only two components that we need. We need the Arduino and we need the USB cable. Everything else we really don't care, because today we just want to make it blink a bit and explore how it works. So yeah, we don't want to go too much into the detail. Alright, so let's get started and connect the Arduino to our computer. Alright, so what I have done is I've connected the other end of the USB cable to a USB port. This is actually some old USB extension cable for a Wi-Fi stick, and yeah, basically I use this to plug in USB sticks so that they can nicely stand on the desk. Now what I am doing is I am taking the Arduino and plugging it in. Alright, so now I have plugged in the Arduino on the other side of the cable, and you can start that it directly lights up, and that you can see that there's a yellow LED blinking. Alright, I've zoomed a bit in so that you can see it a bit easier. This is the Arduino now. You can see it's connected via USB, and you can see it is nicely blinking, same as before. So now let's actually jump into Arduino software. Now this is the so-called Arduino IDE. Well, this might be a bit fast for you if you not have the Arduino IDE. Just open up your web browser and search for Arduino IDE. The first link will probably be it. If the page looks something similar like this, then you are on the right page. You can see that you can download the Arduino IDE for multiple operating systems. I downloaded the Windows version, just the first link. You're going to click yourself through, and then at some point you're going to get a setup, a installer that you can download and install on your system, and boom, you have the Arduino IDE installed. Now, when you are opening up the Arduino IDE, you should get this one, this example, or if you are not lucky and you are getting something else, for example, I think it's also possible that you can get this one. So either you are getting this code, which is called bare minimum, or you are getting this blink code. In case you did not get the blink code, in order to get the code that's initially on the Arduino, you can go to File, Example, Basics, Blink. And if you're opening up the blink example, this is basically what is running on the Arduino when it gets shipped to you. Now you can see there's a lot of text in here, and well, just to quickly explain you, in C++ these are comments. This is a block comment and this is a line comment, and basically you can see that this example has a lot of comment in it. We don't need all this fancy comment, especially the one at the top, so we can quickly remove it, and then we have something to get started with. So this is the initial code that is on the Arduino. Now the Arduino has a certain way of working and writing code. It has two functions. You have the function void setup. This is always going to be there. and you have the function void loop, which is always also going to be there. Now the void setup does exactly what the name suggests. It sets up the Arduino before it's getting used. Now you can see we have a blinking. This is something that cycles through, that loops all the time. Well, this is what happens in the loop. So what happens is a setup gets called once when the Arduino starts, either when it's plugged in by USB, or if I hit the reset button, you can see the blinking stops as continuous on. And if I let go, it, after a short time, it again starts blinking. Well, setup runs and then loop runs. This is basically how it works. Now, if you're familiar to C or C++ or to any programming language, you might be familiar to the concept of a main function. A main function is basically the initial function that always runs. Now, Arduino is not allowing you to gain access to their main function. The main function is actually defined in the code of the Arduino. And just to simplify stuff a bit, the main function works like this. Something similar like this. This is kind of like how the main function of the Arduino works. It calls setup once, and then while this condition is true, and this condition is always true, so it is an infinity loop, call the loop function. This is basically how Arduino software flow works. There might be some additional code that's injected after, before, in between setup, no, in between not, but after setup, or before setup, before loop, or after loop. But the Arduino might inject some other code into that kind of like help to keep up the Arduino's internal systems. That's possible. The Arduino can kind of like have control over the application flow by just providing you a setup and a loop function. In general, setup called once at the beginning, well, kind of suggested because it's on the top, and then loop is called in a repetitive way. Now, what is happening in the loop function? Well, as you can see, it actually reads like English text, digital write, delay, digital write, delay. And if you are looking on what's happening at the board, you might kind of like already get a hunch what's going on. Because, well, digital write, LED turns on in the comment, delay, wait a second, digital write, turn the LED off. So kind of like on, wait, off, wait. And this is basically exactly what's going on. Now let's take a look at the parameters that go to the function. Now you can see that to both of these digital write functions, we are using two arguments. The first argument is called LED built-in. This is the same for both digital writes. And actually, this makes sense because digital write, what do you want to do? You want to write a digital state. Pin on, pin off, voltage on, voltage off. This is kind of like what you do if you are controlling a pin in the digital way in electronics. Well, if you want to write something digital, you need to know where to write it and what to write it. Where do we want to write? We want to write to the built-in LED. This is a constant that's always defined by Arduino if the board has an LED. Well, we have an LED here. There's a built-in LED. Since our board has that, and the Arduino IDE actually detected that we are using an Arduino Uno because, well, we plugged in the Arduino Uno via USB. It detected the Arduino Uno. It knows that on the Arduino Uno, the built-in LED is connected to the pin 13. If we are comparing this to our PowerPoint example, well, pin 13, if we take a look at this, digital function D13 is called the PB5. And if we are taking a look, this LED built in, it's also PB5. So you can see that this built-in LED and the pin 13, they are both connected to the same pin on the microcontroller, the PB5. And well, that is why if we want to talk to the built-in LED, it kind of like resolves to the number 13, which is the Arduino pin number for digital pin functions. Why digital? Because we're using digital write. So the first one is always the pin. The second one is the state that shall be written to the pin. In this case, you can see high is basically just a label for the value 1. In general, we do not really like in electronics to say that we are writing on to an or 1 to an output. We don't want to write 1 to an output because it's a bit confusing, right? If you have an analog and a digital signal, if you are 2 times writing 1, it can has completely different effects. For example, on an analog pin, it might just give you 1 volt, while on a digital pin, it gives you 5 volt. This is why we kind of like tend in these cases to kind of like, define them with different names. For example, high in this case just resolves to a 1 and low just resolves to a 0. And if you know that, it already is very, very simple. So digital write to the LED high, turn the LED on, some delay, and then digital write to the LED low, turn the LED off, delay, again the same value. And well, if you're taking a look at this, The delay function, I think it's kind of like easy to understand. We have a delay, and the delay is actually in milliseconds. Well, what you get is we get a blinking LED. That is 1 second on, 1 second off. It's quite a simple piece of code. Now, how does that come together with this pin mode and the setup function? Well, the setup function sets up the microcontroller for its initial use. Now, since we are using general purpose IOs on the microcontroller, so they are for general purpose, GPIOs, this is kind of like short name for it. The name is already suggesting what's happening. It's a general purpose input output. So either it's an input or it's an output. So you have multiple options for that LED. I mean, for the LED, it doesn't make really sense, but if you would use the pin that's associated to it, maybe you want to control a button with that. Maybe you want to add an external button to that pin, and if you're pushing it, you want to read that the button has been pushed. So, well, you can kind of like use it in multiple ways. This is why it's called general purpose IO. And in order that the microcontroller knows what to actually do, you need to first tell it how you're going to use the pin. This is not only for the microcontroller so that it knows what you are doing, it is also on how to set up the pin. Because a pin is, in general, if it's not configured, it's kind of like floating. Sometimes it's configured to a default state, like by default every pin is an input. But it could also be that the pin is completely floating. So the pin is kind of like not connected to some internal circuitries. And only if you're configuring your pin mode, the pin gets configured in a good state. So it's really important that you know your microcontroller, or in case of Arduino, just tell the pin mode for every pin that you are using so that Arduino can properly initialize that. On a microcontroller, it's a bit different. For example, I know that the AVR by default treats all pins as an input. So if I have a default input and I don't want to change something, I don't need to kind of like specify the pin mode. But it's a different story. We are talking about the Arduino. So Arduino, you're just going to tell the Arduino by calling this pin mode function with LED built in, and output, well, this is the output pin, and then I can digital write to it, I can delay, and I can make it blink. Now, all of these functions, of course, are coming from the Arduino software stack. So if you are doing plain AVR code, you are not going to have these functions. For sure not. Now let's play a bit around and see how we can affect the program. So the first thing that I want to do is I just want to make it blink faster. I want to blink it 10 times faster. So basically I'm just going to remove a 0. Now if I remove a 0, you can see that, well, I have now write delay for 100 milliseconds, write 100 milliseconds delay. Now when I finish writing a program, I have multiple options that I can do. If I press Ctrl S, of course I can save my program, but that's not really required. Now what can I do with my program is finished. Now there are actually two options that are available on the Arduino Udo. The first one is the button above here, it's verify, and the second one is the button upload. Now upload basically means compile this code into the binary representation and send it to the device selected in this dropdown. In this case, you can see that I have the Arduino Uno, which is connected to something called COM7, which COM7 basically means is a serial interface, so it's a virtual serial port. Basically, there's USB, this chip that's on here that's basically emulating a serial connection, because, well, the Arduino, of course, it doesn't speak USB, but this chip does. This chip does speak USB, and the software on this chip is luring the computer into thinking that it has a serial RS-232 connection connected. It's not really always RS-232 because it could be multiple ones, and there's a bit more to it than just RS-232 versus COM ports in general on Windows. But in general, it kind of like emulates a very, very old but simple interface. And this simple interface is used by the Arduino IDE to upload data. Now, if you don't want to upload the data directly because you're working offline and you don't have a microcontroller at hand, you also have the option to just verify the program. If I click on verify, it's basically just compiling that and giving me some information on that application. Sadly, this is in German. I don't know. My main language here is English in the PC. I just have a German keyboard layout, and somehow this German keyboard layout is messing up the output of the Arduino IDE, but that's not too important now. For now, I just want to show you quickly how it's done. So basically, when I compile it, it gives you a few informations. For example, it tells you how much of the Programmspeicherplatz, which basically means data flash, is used. For example, this application, including all the features that are implemented in the Arduino IDE that we are using, not the IDE, the Arduino software stack. So like everything, like the main loop from Arduino, this pin mode function, the digital write function, the delay function, the main function from Arduino, All of these plus the code that I have written takes 922 bytes, which is equal to 2% of my total 32K of flash storage. Now, if we're taking a look at dynamic variables, so the dynamic storage, the RAM, the random access memory, you can see that from this one we are only using 9 bytes, which is equal to a bit more than 0% of the maximum of these 2 kilobytes. So actually you can see that this application, it nearly needs no RAM at all. On a computer, if you would want to do something similar on a computer, you would already use quite a lot of more RAM just for the application, not just 9 bytes. And these 9 bytes that we can see here are actually coming because we are using the Arduino software stack. If we would run the same code, just blinking LEDs, on a bare metal AVR controller without the Arduino software stack, we would be at 0 bytes. The thing is that inside of this digital write and pin mode functions that I can actually look into, if I right click on them, go to definition, it opens actually the implementation, how the function underneath works. You can actually see that in here there is memory use. So for example, in this case, what I'm doing is I'm actually having 2 8-bit numbers, and I have 2 pointers to 8-bit numbers, and these kind of like symbols, they take away memory, and this pin mode function therefore needs like 1, 2, I don't know how big pointers are, but probably 16-bit on the Arduino, so like 6 bytes are required by this function. And maybe down here it needs there's another byte that's required, so you can see we are kind of like at 7 bytes, and you can see, yeah, that this kind of like consumes memory, these functions, internally. But that's not too much of your concern, right? You just see that you have 0 and 2%, which is nothing in the end, and well, it makes the application blink. No, not yet, because I haven't uploaded it. Let's now click on upload. When the Arduino Uno is selected, it will automatically flash to the Arduino, and now you can already see on the camera that it's blinking faster, right? If we go full screen, it's maybe even better to see. Previously it was blinking quite slower, now it's blinking fast. And maybe to make this even more noticeable what we are doing, well, we could even make a odd number. So let's maybe put it high for, let's say, 250, and let's put it low for 750. And if I change it to that and then hit upload, we're basically gonna have some flashing. So you can see we have some flashing. Maybe the flash is a bit too slow. Let's maybe do something like 150 and upload it. This is, I think, a bit more flashy. Still a bit too slow for my taste, flashing. High should be maybe just 50, right? I want to have fast flashes. Yeah, this is a bit more what I'm thinking. It's not really noticeable on camera, but in reality you can actually see that it's kind of like a flashing light. This would be something that you might want to have if you are building like some indication device and this indicates an error. You have these like these short flashes of red on a status LED that tells you that there's something wrong. So yeah, as you can see, we can very, very easily go in and change the software of this code. Now, what I want to now do is I've promised you that we're going to improve it. Now, well, basically, how can we improve that? Now, let's jump back to the original use case of just having some normal blinking numbers. So normal blinking, some even on and odd times. So same on the time than off time. Now what we can do is similar to how the Arduino uses this LED built in, we can use the same technique to kind of like define ourselves constances or parameters of our application. So for example, what we have is we might have a really big application that uses this delay multiple times. So the actual delay time in between the blinks, it's used like in, let's say, 20 different locations in the code. And if we want to change it on one side, because, well, some UX designer from our product comes to us and says, all right, the flashing is too fast. It's not nice for the people. We are building home appliances. This flashing makes the people aggressive. They don't like this fast flashing. We want to make it slower. Well, you then need to go through all of the code and you need to catch every occurrence where you can see this 200 and it's the right place and change it back to something like 500. And this is not, of course, how you want it, because you cannot just control F for 200 because, well, there might be other 200s in the code. Also, not all delays might be related to this blinking of 200, or there might be some fault where we want to have that aggressive blinking so that the user really know that something is off. And therefore, what we want to do is we want to kind of like declare ourselves a parameter, a constant. Now in C, we can do constants like that. Const int delay time. For example, we could declare it like that, delay time, and set the delay time to 500. Then what we can do is we can take this delay time and we can paste it everywhere. Now you can see we are currently using 9 bytes. And if I recompile, we are still using 9 bytes. However, it could have been that this delay time actually would have used a byte. But in general, we don't like to do this because this delay time now looks like it is a variable. However, some parameters like these, you can see they also have defined the LED built in, not like an int. If I go to that, you can actually see that the LED built in is defined in a whole different way than how I defined the delay time. And this is like the proper way of doing it. Now, compilers these days are really smart. A compiler sees that this value is used in the same way as this one and removes kind of like the overhead that this one would have. Because I can actually lure the Arduino into thinking that this is used somewhere else. Now, just by changing the const keyword to this volatile, you can see that we are using more bytes. And old compilers were not able to deduce this, maybe. So you can see now 11 bytes versus 9 bytes, just by changing a keyword, just changing a random word in our code. And this random word basically gets optimized away by the compiler. If we are taking this volatile that I had in previously, it kind of like tells the compiler, you don't know what's happening here, so just leave it untouched. However, this const, it kind of like sees that it's used the same way than this LED built in, and it is optimizing that away into a constant. However, it could be different. So what we tend to do is we are tending to use the preprocessor and use this hashtag define. Hashtag define is a keyword. Now after this define, we can give it a label. So our label will be LED on off time. And the on off time is 500. Now the nice thing is that this hashtag define can be anything, right? I could even hashtag define something like LED delay and replace this with the delay call and the LED on off time. I could even make this one look like a function call. And then instead of delay, I can say something like LED delay. That's also possible, right? This hashtag define is a very powerful tool that helps you to make the code way easier, way modular, and also way more universal, because the LED delay might be implemented in different ways. Now you can see we have back the old blinking, not the old Arduino blinking, but a different speed of blinking. Now, again, this is kind of like all magic that happens, because basically what these hashtags defines are, they are copy and paste symbols. So if the compiler, or not the compiler, is actually happening before the compiler, with the so-called preprocessor, but I don't want to go too much into the detail how the C++ language work. You should know that. Basically what the preprocessor is doing, it is seeing this label, this LED delay, used like a function, and it searches in its tables if it has been defined. And you can see LED delay was defined as a label. And basically what it does is, instead of that, it copy and pastes this in here. So instead of LED delay, it copy pastes this in here. Now in the next step, it will go further. It will see a right LED on off time. Is this defined? Yes, it is defined up here. And basically what the preprocessor does, it copy and pastes these like defined symbols into your code. This is never like copy and pasted in the real file. This is all just virtually happening in memory. And after all these copy and replace have been done, actually what happens is that then the code gets compiled, and then in the end it sees no const int, for example. It does not even see that, it just sees a constant just in place. And especially if the code is more complex and it's getting obscure for the compiler, and the compiler might not be able to deduce if it's safe to optimize your const or your variable, like your int delay, even if I would just make this an int, right? If I would just make int delay and I just delay on the int, it will probably still use 9 bytes. I have a problem. Where do I have a problem? Because I cannot call this the same than the function. So if I just do int d here, you can see it's still using 9 bytes, because the compiler is actually looking and seeing, well, this value is one time assigned, it's never changed. And it optimizes this away. But the more complex the code gets, at some point it can be that the compiler can no longer decide if this can be optimized away. And then the compiler will start not optimizing it away, and you're using memory that you would not need to waste. This is why on embedded systems we like to do it with these hashtag defines. We don't want to overdo this with this LED delay. This is definitely not something that we want to do. We rather do this with times. The same also goes for things like high and low. How do we know that the LED is really on when it is high? Connecting an LED to the microcontroller can be done in multiple ways. Currently, we have the 5 volt that are coming out of the microcontroller, that are flowing over an resistance, that are flowing through the LED and to ground, thus making the LED light up. However, you can also connect the LED the other way around. You can actually take 5 volt, connect it to a resistor, connect it through an LED, and connect it to the microcontroller pin. Then the LED can only turn on if the microcontroller pin is low, so connected to ground and not connected to 5 volt. So how do we know which is the LED on and the LED off state? Well, we can also define ourselves this. So LED level on. So what is the level of an LED that is on? In our case, it's high. Then LED level off. What is the off level? Low. Well, then we can even make it even simpler. We can replace this with LED level on and off. So we have the on level and the off level. We are writing to the built-in LED the on or the off level. Built-in LED, the next thing that might be a problem, right? You want to make your code exchangeable, or you might even want to make your code compatible with multiple circuit boards. So you might have a built-in LED that is on a different pin. Of course, you could redefine this, but this LED built-in is kind of like an Arduino thing. You might have multiple configurations of your code for platforms or for features that put the LED on different pins. So what we also want to do is we want to define our LED pin, and our LED pin is the LED built-in. So what we now can do is we can replace this to the LED pin. Same goes here, LED pin, output, LED pin on, delay on the on-off time, then the LED pin is off, and we delay again. Now this code is not doing anything differently than the code that we had previously. It is just making our code a bit better. Now, you would probably think, do we need this? Well, most tutorials will not teach you that on the Arduino. Some of them do. Some of them go into that and tell you actually that you should put everything that's kind of like a parameter up here, because if you're changing your LED to, for example, pin 8, well, you change the 8 here and upload the code, and now the LED is on pin 8, which of course means that we no longer get a blinking because it's blinking a pin that has no LED connected. But if I would go in with my multimeter, which could actually be quite a good kind of like a good opportunity to maybe showcase the multimeter. So if I put my multimeter next to it, like this, I might be able to probe the pin and see that it is really on. This might be a bit hard because I'm using pin 8 and I don't think that I have access to that pin 8, but we could maybe quickly find out where the pin 8 actually is. If I go to Arduino pin out, I might find something. If I go to images, that actually show us how the pins on the microcontroller are located. Maybe I don't see something like that. Yeah, there it is. This is what I was looking for. So I put this to the pin 8, which interestingly enough, how does it not map to a pin? This is the number of pin. Okay. Digital pin 8. This is the digital pin 8. So this is the kind of like top of the microcontroller. Now you cannot really see it. The digital pin 8 is down here. So this is the notch of the microcontroller. This is kind of like the top side. And if we are going on the notch, the dot that's on there, to the complete other side, we are at pin 8, which also works on the board. You can, for that, we can zoom a bit in. Where do we have ground on the microcontroller? But I think ground is kind of in the center, but I think we will be able to find the ground just by randomly poking around the board. I'm not sure. Can we find the ground quickly? There's no like, I might need to eyeball it. This would be, ground would be pin 8. So pin 8 is the same than 8, so 8 and 14. Let's see, pin 8 as a ground. And then if we would go to the full screen, there you can see directly next to the multimeter is the notch of the microcontroller. Now I'm pulling the microcontroller with the wires of the multimeter, which is not so cool. But yeah, I have my multimeter in voltage mode so that it measures voltages. And what I now want to go is I want to poke to the pin 8, which is the ground. So pin 8 is kind of like starting to count from there. This is kind of like the first pin. They would need to count to 8 there. But let's first position the plus, because I need to actually bend quite over to get my leads in, which is here. This is the topmost, is the one that we are controlling. And now I'm going to try to catch the signal. This one as well. Yeah, there you got it. I think you quickly saw the blinking, right? You saw the blinking on the multimeter because the 4.5 volt and the 0 volt. I did not really get a good contact there. So now I've basically moved it to the pin. So let's put it back to LED built-in. By the way, if you want to have this autocomplete, you start typing, you press Control Space, and it's going to give you all the symbols. For example, this LED built-in. Now let's put it back to LED built-in, and you should see that the normal LED is blinking again. Ah, you didn't saw my screen, right? What I was showing you with the autocomplete, if I do like start typing, Control Space, it gives me all of the stuff that's kind of like defined with that name. Also, for example, pin mode, if I do pin M, pin mode, and you can also see the documentation like pin and the mode that's kind of like used for it. So yeah, this is kind of like super handy that you can do this with the new Arduino IDE, which I think is more or less Visual Studio Code. I'm not sure. But it looks kind of similar to Visual Studio Code. It has kind of similar ways. I don't know. No, it's copyright Arduino. I don't know how they have built it, but it's kind of similar to Visual Studio Code and how it works. But yeah. Now basically this is the normal LED blinking from Arduino expanded to our use. We have talked about the dev kit. We have talked about the board. We used the multimeter today to do a bit of probing and poking around, which I think is kind of good for the first video. I think, yeah, it's quite prolonged of the blinking. But yeah, I think it's useful, I hope. And yeah, thank you for watching. See you in the next video where we're actually going to connect the external LED and make it a bit more fancy. So then, stay tuned. Until next time, have a nice day. Bye.